Okay, hi everyone. My name is Stefan Vuckovic and I'm a postdoctoral researcher at the University of California. So I work in the group of Kieran Burke. And here, first I want to thank organizers for inviting me to speak here. And I'm going to talk about non-covalent interactions. Uh, Non-covalent interactions, oh, it's needless to introduce them, how important they are. They are omnipresent in chemistry, biology, materials, and often when it comes to treatment of non-covalent interactions, smaller placid perturbation theory, it is often considered qualitatively suitable for modeling non-covalent interactions. On the other hand, semi-local DFT for those interactions are often erratic. And now we can ask, okay, what are the things that support the wide usability of molar placid perturbation theory? Most often MP2, because anything higher orders such as MP3 and MP4, they are often unaffordable. So when I speak of molar placid, usually MP2 is used to treat these kind of systems, and what are the advantages? What are the reasons why people consider MP2 good enough to treat non-covalent interactions? First, it shows the correct asymptotic behavior, 1 over r to the power of 6 of the dispersion energy. It is size extensive, and for small systems, the convergence of the molar placid series is very fast. So, but I emphasize here small system. Later, we are going to see why. And a natural question that arises, are these conditions sufficient to consider molar placid fundamentally adequate for the non-covalent interactions? And recently, lots of the failures of MP2 when applied to large molecular systems have been shown. For example, I show here the L7 dataset, which includes like 7 relatively large molecular complexes. And the relative errors of MP2 can be really high. Here, for example, in the guanine trimer, which is here stacked as in DNA, the relative error of MP2 binding energy is more than 140%. If one goes an order higher to MP3, which comes at much greater computational cost, the error is still a little bit lower, but it's still around 80%. So it's still not of use. And a question that arises here, are these failures of MP2 and MP series in general, are they accidental or are they more systematic? This was recently explored in a paper of Philip Ferk and his group, where they found that while for small molecules, MP series converges fast, at least when one looks at the interaction energies. For large molecules, the MP series actually diverges. Also, another thing shows that regression analysis reveals a systematic increase of relative MP2 binding energy errors with the system size at a rate of approximately 0.1% per valence electron. That means the larger the molecule you have, the greater the error in binding energies by MP2 you can expect. Okay, so there are also lots of methods that are built upon MP2 that are widely used in quantum chemistry, such as spin component scale MP2. But all of these methods, they inherit the problem of MP2, and their errors also increase with the relative errors increase with the size of the system. And okay, so here I'm going to talk about how this problem can be fixed. And to do that, first I'm going to introduce the so-called Hartree-Fock adiabatic connection. Uh, this is the adiabatic connection in which the molar placid series arises. To do that, I introduce the Hamiltonian h lambda on the right-hand side, where lambda is the coupling scale constant that scales the electron repulsion. And I also denote by psi lambda a wave function that minimizes this Hamiltonian h lambda. And okay, one can wonder what happens when we set lambda to 0. Then we get a non-interacting system. Basically, we kill the electron-electron repulsion. Our h lambda becomes the Fock operator, and the underlying wave function is just a single Slater, determinant. On the other hand, what happens at lambda equals 1? Then we kill the j and k terms, and basically we get the physical Hamiltonian, and also the psi lambda at lambda equals 1 becomes a physical wave function. And okay, if we plot something, what is called the adiabatic connection integrand, which connects the Hartree-Fock at lambda equals 0 and physical wave function at lambda equals 1, we can get the exact expression for the correlation energy in quantum chemistry. And it's going to be given by the area above this integrand. And the integrand is going to be given by this equation here. And this is what one can easily obtain when applying the Hellman-Feynman theorem to the Hamiltonian h lambda. And okay, so we got this expression, basically this area above the AC integrand exactly gives you the correlation energy. One thing is at low lambda, the molar placid series arises, and the initial curvature of our black adiabatic connection AC integrand is going to be given by 2 times the correlation energy of MP2. Recently, what has been also done, one asked the question, okay, what happens when this lambda goes to infinity of this specific adiabatic connection theory? And it has found out that as lambda goes to infinity, when the coupling constant, when the electron repulsion is scaled to infinity, then in that case, W infinity, this quantity here, as in DFT, it actually becomes a functional of the Hartree-Fock density. So basically, it can be constructed easily once only after you perform the self-consistent calculation. Okay, one can ask here a question, why is this the whole Hartree-Fock adiabatic connection that I presented here, why is it useful? Because to compute the correlation energy given by this way, it is actually more expensive than solving directly Schrodinger equation. But at the same time, it provides a very powerful route for building approximations. Okay, so here I will give the main idea, like how we have used this to build approximations and how to correct MP2. So the whole idea is, okay, MP2 arises in the small coupling limit. What happens if we want to include information from the other end? Basically, if we want to include this W infinity limit, which comes from the strongly correlated end of this adiabatic connection, how we can do that? Okay, so the key idea here is to construct an approach which basically does an interpolation between the blue line given by MP2 and the pink line given by the strongly coupling limit of the Hartree-Fock adiabatic connection. And to do that, here we employ an interpolation formula. This we borrow from DFT. This formula has been developed by Seidel, Perdue, and Levy. And it enables us to do interpolation between the two limits. Next, Okay, this W infinity, we need a reasonable approximation, so it costs little to compute, and we have found in this paper that it can be accurately and approximated by this simple integral over the Hartree-Fock density minus the exact Hartree-Fock exchange. And one problem that this equation, SPL, has, it has suffered from size consistency in DFT that has been well known. Like if you build a model for the AC integrand that depends non-linearly on the ingredients, then you have a size consistency problem. However, we recently showed that this size consistency issue with this adiabatic connection formula can be easily fixed. And here in this paper, we have proposed a way how to do it, how to restore size consistency. And for example, here on the right-hand side, I showed the errors of dimers involving noble gases of certain adiabatic connection formula before size consistency correction is turned on. These are the errors, the red ones, and after you turn them, and after you turn on the size consistency corrections, basically all the errors go to zero. So this slide was just to show that these models, the size consistency issues can be easily fixed within this framework. Okay, so I go now back to the slide. Okay, so here I give a list of things that I need to compute my, to construct my approach. And basically, what are the ingredients that I need for that? I need ECMP2, which one obtains after an MP2 calculation is run. I need the exact exchange. That's also included when MP2 calculation is run. And what else I need? I need this integral over the Hartree-Fock density. That basically comes at negligible cost in relative to the MP2 calculation. Computing this formula, once you calculated the ingredients, takes a fraction of a second. And finally, size consistency correction comes at no additional cost, meaning that the whole thing basically comes at, the whole procedure requires no extra cost other than the cost you need for an MP2 calculation. Okay, so this method, like the procedure based on the Hartree-Fock adiabatic connection, where I attempt to correct MP2, I call here SPL because that was the formula that we used. And I show you here the results for the S66 data set. So the black, these are the errors for the S60 data set. And I also compare with MP2 and B2 PLIP. For systems bounded by dispersion, the performance of SPL is much greater than that of MP2. For example, here you have pi-stack systems where failures of MP2 are well known, and these errors are substantially reduced when SPL is included. And we have also used this SPL form to build a diagnostic tool for MP2. How it works. Okay, so here by black curves, I show you the, let's say the black curve is the exact AC integrand, whereas the MP2 is the one that comes from MP2. The blue one is the one that comes from MP2. And it is always a straight line. So one can ask the question, okay, when MP2 is accurate? And basically, the more the linear, the black, the exact curve is, the MP2 is going to be more accurate. And so this is the case when on the left-hand side, when the exact curve is quite linear, whereas as the curvature of the exact curve is highly pronounced, then the MP2 fails to describe this. And okay, so since we found out that the stronger the curvature of the exact curve, the less accurate the MP2 is. We have constructed this MP2 accuracy indicator or map, which is dimensionless measure of the adiabatic connection curve curvature. And when map goes to 0, that means that the AC curve is perfectly linear, which in turn means that MP2 has no errors. Okay, so now I show you how this works in practice. On the x-axis, I plot the map values, which is the MP2 accuracy predictor. And on the y-axis, I show you the MP2 relative errors in binding energies of the S60 dataset. Here we can see the correlation. Basically, as map increases, the MP2 relative error, they also increase, and roughly somewhere here, when map is greater than 0.20, the curve, the relative error of MP2 become very big, and it is basically of no use. Okay, so one can wonder what are the typical systems where map is low. These are, and when these are those bonded by, so here I have acetic acid dimer. This is where map is low, meaning that MP2 relative error is also low. But when you go to systems where map are large, these are typically systems bonded by dispersion. And specifically here I have benzene dimer. And this is the case where map values are high, and at the same time, the MP2 relative errors, they are basically skyrocketing. We have also found the correlation between map and the dispersion electrostatics ratio from symmetry adapted perturbation theory. We have found that the higher the dispersion electrostatic ratio is, the greater the map values are. That in turn means the greater the map values are, the more pronounced AC curve curvature is, which in turn translates to lower accuracy of the MP2. Okay, so what I showed you so far, it was about this SPL construction and what are its advantages. It is overall much more accurate than MP2, and it also has enabled us to construct this map as an indicator of deficiencies. But also here I want to discuss what are the deficiencies of this SPL. Okay, so if I define here delta EC being the difference between the true correlation energy and that of MP2, this is basically the MP2 error. And I show you here for a variety of data sets. On the x-axis, I plot what should be the correction to MP2 correlation energy. And on the y-axis, I show you how it's predicted by our theory. So one can see that at small delta EC, it works quite well, whereas as you increase delta EC, it starts to deviate from this black line, meaning that it is still better than MP2, but there is still lots of room for improvement. Okay, also, if I zoom in the plot around 0, we can see that when MP2 overbinds, it does quite good job in reducing that error. But when MP2 underbinds non-covalent complexes, it corrects the MP2 in a wrong direction. Okay, this is not too bad because MP2 most of the time overbinds complexes when you use big enough basis set, but still there are some cases when even there the MP2 underbinds, and this needs to be corrected. Okay, so we wanted to fix these deficiencies, and how we did that, we first realized that we need a more flexible form than SPL, more flexible interpolation form that we want to use to build to build our approach. Okay, so here we introduced a new form, and I call it here SPL2 because it contains two SPL terms. And this form has 6 parameters. The 3 ones are the same as in SPL, and we fix them by these 3 exact constraints. However, the three uh, the remaining 3 parameters, we trained them on the S22 data set. We have found out that we are also almost reaching the accuracy limit for a given form when we don't use any empirical input. And for that reason, at this point, we have decided to introduce some empiricism, and therefore these 3 ping parameters, we train them on the S22 data set. And okay, so here I show you the same plots, but where I also include the new form, which I call here the SPL2, by the green dots. It shows that it improves. In this parity plot, we can see that it much better predicts the correction that is needed to MP2 to be more accurate. And also, if we look in this region around 0, uh, one can see that it is able to correct MP2 when it both overbinds and also to correct it when it underbinds. And remember, that was a shortcoming of our previous model, which was the orange dot. Okay, so I show you here some results. This is for the krypton dimer, and our SPL2, it's better than SPL here, which was our previous form. It's better than MP2. It's also better than B3 lip, and B3 lip when the D3 correction is applied. And it also, of course, it's much better than B2 PLIP, which is here a representative of a double hybrid. So I stay with the same figure, but I removed all the other approaches except for B2 PLIP and SPL2 because I want to highlight the difference between them, because given its form, SPL2 can be considered a double hybrid because it contains the exact exchange, it contains the MP2 correlation, and it also contains that DFT part. However, there are 2 key differences between SPL2 and standard double hybrid functionals such as B2 PLIP. The first one is that SPL2, it uses the full exact exchange and the full MP2 correlation. And for that reason, it does not rely on the error cancellation between these quantities and their semi-local counterparts. For example, in B2 PLIP, you have the MP2 correlation, but also you have a fraction of semi-local lip correlation. Another difference between these 2 approaches is that SPL2 requires no D3 correction to be accurate for non-covalent interactions. And we can see this is definitely not the case with standard double hybrid functionals, because here B2 PLIP, if no D3 correction is applied, it is basically gives a repulsive curve. Okay, so here I go to L7 data set, which I showed you at the beginning, and I show you the results for different theories. For example, SPL was the one, our previous model. It is greatly improved by SPL2, whose relative error is only about 5% in comparison. The relative error for MP2 is 60%, and in this way we are 12 times more accurate than MP2. And it's important to remember that SPL2 basically comes at no extra cost in addition to that of MP2. Okay, so here are more.
5 more minutes now.
Okay, 5 more minutes to talk, or
5 more minutes in total.
Okay, so I'll just need 1 minute to finish it off.
Okay, you used your first 25 minutes.
Okay. So here I show you some results for the benzene pyridine dimer. Our SPL, the green curve, still does good. However, here DFT D3 lip is also quite good. However, when we go to hydrogen bonded complexes here, this is the this is acetami dimer. SPL SPL2 is still good, whereas the accuracy of B3 lip D3 significantly deteriorates. Okay, so here I will give a summary. Our SPL2 construction is highly accurate for non-covalent interactions. On the other hand, MP2 has fundamental issues when applied to non-covalent interactions. And with SPL, we fix them at no additional cost. There is also still room for the accuracy improvement. One can consider more sophisticated interpolation forms. A key advantage of it is that it can be easily implemented in any code that already has MP2 package. And in the future, we will also consider different cost lowering strategies, such as linear scaling MP2 to reduce the cost of the MP2 part, which is the bottleneck of the SPL2's cost. And we will also try some MP2 replacements which try to approximate MP2 by avoiding double summation over virtual orbitals. Okay, I'll skip this, and I want to thank you for your attention and my collaborators who worked on this project.
Thank you very much, Stefan, for this presentation. We now have time for a few questions. I don't see anybody having any questions.